My name is Longqing, and I'm a doctoral student majoring in CFD in Peking University. And today my topic is about our CFD solver applicable to non-equilibrium flows, KTMR. It is now open source on GitHub, and we welcome you to explore it. And firstly, math time. Let's keep it light, and I won't go too deep. I'll just give a simple overview of the theory so everyone can better understand what we are doing and why. You may already be familiar with traditional CFD solvers solving the conservation variables of the Navier-Stokes equations. In contrast, kinetic methods solve the distribution function in Boltzmann equation, usually in its model equation. And a distribution function typically looks like this in velocity space. Despite appearing simpler and having fewer variables, the distribution function operates in a higher dimensional space, making it challenging to solve. Integrating the distribution function yields the variables of interest in fluids. Discretizing the velocity space allows for direct numerical integration, which is one of the most popular methods called DVM. Because kinetic methods describe flow at the molecular level, they are more fundamental and universal, but computationally expensive. However, these calculations are well suited for parallel processing, especially on GPUs. And with more and more powerful GPUs available, we believe it is time to do it. So KTMR. Oops. What's wrong with it? Yeah. KTMR, in essence, it is a large-scale distributed adaptive kinetic CFD solver. Our expectations for it are primarily focused on three aspects. In terms of scale, it features distributed parallel capabilities and adaptability. The most noted feature is that we have achieved synchronous adaptability in velocity and physical space, which is really crucial for large-scale kinetic simulation. Additionally, it will leverage GPU's differentiable programming, machine learning, and other technologies to enhance solving efficiency. And you know, all of them are areas where Julia excels. And regarding automation, we use Cartesian grids managed by quad or octree, known for their advantage in automated generation. And the post-processing capabilities are also integrated. And for applicability, KTMR is based on kinetic methods, specifically supporting DVM. Certainly, we will also implement other fluxes based on kinetic methods, and to address the shortcomings of Cartesian grids in adapting to boundaries, we will introduce the newest immersed boundary method to accommodate a wider range of boundary types. What's wrong with this? But unfortunately, the development of the solver is still in its early stage due to my busy schedule over the past year. But the green sections highlight functionalities we have already implemented. Could you help me? Okay. Since the user interface is not ready yet, KTMR is temporarily unavailable in package, but it will come soon. Just stay tuned for updates. And this is an example of non-equilibrium flow often used as a benchmark, which is solved by KTMR. It involves a square cavity where the lid moves to the right, driving the flow of gas inside. While not the most ideal demonstration of adaptive meshing, you can still clearly see the changes in the grid. The left video represents velocity space within a single physical grid, where they evolve synchronously during the flow process. And simply put, regions with higher distribution function velocity space require denser grids. In some extreme cases, the distribution function may move here or there, and to maintain, without adaptability, to maintain computational accuracy, the entire velocity space requires grids as dense as those areas the most dense, and in steeper cases, even denser. And this is just within a single physical grid and in only 2 dimensions. Now you can imagine how terrifying the computational cost would be. Thus, adaptive refinement in velocity space is crucial, and the situation is just exactly the same in physical space. And for this case study, we increased the grid scale. Scale is still not large, but anyway, we tested the solver's strong scaling on this grid. The serial proportion accounted for only about 0.36%, and achieving an about 80% efficiency boost on 128 cores. Given the grid scale, these results are quite satisfactory. Well, developing a distributed parallel tree structure program from scratch is quite daunting. And unfortunately, I couldn't find a suitable Julia package for this task. But thankfully, Julia has excellent interoperability with other languages, so I turned to Carsten's P-Forest, developed in C code. Personally, I find the rules for Julia's interaction with C somewhat complex, but once understood, the process becomes quite enjoyable. Roughly speaking, P-Forest primarily provides the topological information of the tree grid, while most data and computational process are handled by Julia. The efficiency of solving is minimally affected by the interaction between Julia and the C. It is worth noting that the tree grid for velocity space was independently designed by myself, which I'll discuss later. Another crucial consideration when handling C functions is that Julia data passed into C functions are not visible to the garbage collector. Without GC preserve, Julia data can be prematurely collected, potentially leading to segmentation fault errors, and your IEPO will crash immediately, which was quite confusing and became my biggest nightmare during early development. DVM is quite different compared to traditional methods. Due to each physical grid having its own velocity space, the main feature of DVM is its significantly larger data size compared to traditional CFD solvers. This implies more costly inter-process communication and stricter memory requirements. To address this, our strategy involves redundantly computing fluxes at interfaces between adjacent processes. Computing the interface once is much faster than communicating it. To provide a better understanding of the memory requirements of DVM, here are some figures. For the moderately sized 2D grid I mentioned earlier, storing the data requires about 70 gigabytes. Additionally, storing an extra double type per velocity space grid increase the data size by about 4 gigabytes, making it quite expensive. Therefore, we have streamlined the tree structure information of the velocity space as much as possible. This streamlined implementation benefits from the second characteristic of DVM. The functionalities used in the velocity space are very basic. They only need to establish correspondences with neighboring physical grid velocity spaces and locate their siblings to facilitate grid coarsening. The velocity space tree grid I designed ultimately only requires an 8 type level information combined with Z ordering to achieve the above functionalities efficiently. This is also aided by Julia's efficient optimization for loops. But interestingly, even after a full garbage collection, the program's memory usage is significantly larger than the data size. Why is it? Well, I found during the adaptive processes in velocity space, areas need to be resized. Therefore, Julia allocates additional buffers to accelerate this process. Given the substantial number of these areas, the size of these buffers can become burdensome. And currently, Julia does not seem to offer a good method to release this portion of memory. Perhaps the only option is to sacrifice efficiency and copy the data into areas of exact memory size after each adaptation. This is something we need to consider moving forward. Suggestions for improvement are really welcome. And that's all for my talk. Thanks for listening, and welcome to visit our repository.
Thank you. A round of applause for Ge. I don't